So the question is about the name of the method. Just a moment, please. I prepare the response, but I don't save the slide, so I will search this response on the textbook and I will share my desktop. Just a moment, please. Do you see my desktop? Okay. So for your question, BUG stands for button-up construction. However, according to the latest convention described before and used through this book, the BUG processing order is actually top-down. So the order is top-down. Okay, Mr. Abdul Wahid. But the BUG authors view a lattice of cuboids in the reverse order. So the authors of this method view the lattice of cuboids in the reverse order. For this reason, in the reverse order, that means with the apex cuboid at the bottom and the base cuboid at the top. In that view, BUG does bottom-up construction. For this reason, the authors say that it is a bottom-up construction because they view the lattice in reverse order. It's clear? Good. Okay, so in this session we will continue with online query competition. So the query has the general form A1, A2, A3, AN, M. So what is A1, A2, A? This part, what represents? What represents this part? Attributes, not attributes, but we can talk about dimensions. Very good. And M here, M is the measure. It is clear? Okay, so this is represent a query, online query. And HAI has three possible values. Instantiate value, that means specific value. Aggregate star function. So star in the query, that means irrelevant for us. Okay? And inquire with interrogation mark, that means required. Inquired. I repeat. So the value of AI, the value, for example, of A2 can be instantiated value or aggregate star function or inquired function. It is clear? Okay, so this is an example of a query. Can you explain me this example? So in this example, how many dimensions, or how many, if you can say how many dimensions? Yes, how many? 6? Not 6. So here in this we have 1, 5. Very good, Mr. Nabil. 5 dimensions here. We have 5. So this is the first, second, third, fourth, fifth. 5 dimensions and measure. Okay, so in this query, the first and the fifth dimensions values are instantiated. So the first, let's get, for example, the green for instantiated value. In our example, this 3 and 1 represent instantiated value. That means for the first dimension we want that A1 equal 3, and for the fifth dimension we want that A5 equal 1. It's clear in our query. Okay, and the fourth is irrelevant. The fourth one is irrelevant. For example, let's represent the fourth by blue. The fourth is irrelevant. That means the return or the result of this query, we don't need the fourth dimension. For this reason, in our query we note this dimension by a star. It is clear? Okay, and after that the second and the third are inquired. The second and the third are inquired. So here we have second and third. So for this reason, the result of this query will be a subcube that computes all possible value combination of the inquired dimensions. All possible combination of the inquired dimensions. For this reason, this query returns a 2D data cube. It is clear? Last point, that means what? Inquired. Okay. So here we talk about a query, and the result of this query is a data cube. So the dimension of the results, it depends of the number of dimensions that are inquired. So in our example, we have the second and the third dimensions are inquired. For this reason, the return will be a two-dimension data cube. So the result will be all the possible combination of this inquired dimensions. Why? Because the first dimension is fixed. We fixed it at 3. The last dimension at 1. The fourth dimension is irrelevant. Yes, of course. So the measure will be the count here in our case. For this reason, here the last argument is measure. Now, because we have two inquired, not two instantiated, two inquired. Instantiated, that means for all the possible values, the A1 will be 3. A1 is fixed by the user. If we want to make a similar SQL query like this, a similar SQL query, it is like say select name. So name is inquired, and name and age. Age is also inquired from structures where ID equal 3 and experience equal 1. So ID and experience are instantiated, are fixed. So the result of this query will be a data cube with the inquired dimensions. It is clear? Yes, in my example of SQL is names and age. But here we talk about a multidimensional. Yes. So here I've instantiated are in green. 3 is an instantiated value. That means fixed value. That means the first dimension must be equal 3. So the result will be with the first dimension equal 3, with the fifth dimension equal 1. It is clear now? Welcome. Let's move now to online query competition. The method, how we can make online query competition. So given the fragment cubes, process a query as follows. The first step is to divide the query into fragments, same as the shell. After that, we fetch the corresponding TID list for each fragment from the fragment cube. After that, we make intersection, so we will intersect the TID list from each fragment to construct instantiated base table, and finally we compute the data cube using the base table with any cubing algorithm. So there are 4 steps to make online query competition. The first one, we divide the query into fragments, same as the shell. The second one, we fetch the corresponding TID list for each fragment. We will intersect the TID list from each fragment to construct instantiated base table, and after that we will compute the data cube using the base table with any cubing algorithm. So this is a schema of online query competition. Okay, so I will explain this method through an example. Okay, so I will explain this method through an example. Just a moment, please. So let's suppose that our query is like this. A2 B1 star count. So this is my query. Okay. So how many dimensions the result of this query will be? How many dimensions? A cube with 2D. 2 or 5? 2. Why 2? Two represent what? Yes, we have 2 inquired. 2 inquired. So this is a query, Mr. Nabil. So this is the first dimension. This is the second one. It's clear? Okay. So how we will make the competition of this online query? So the first step is to divide the query into fragment same as the shell. So here, for example, this is my first fragment, A1 B2. This is the second fragment for C, and this is the third fragment for E. So here we have A, B, here C, and here E. So for D is irrelevant. For this reason, we can remove this fragment. We can not consider this fragment. Okay, this is the first step. So the first step is to divide the query into fragments same as the shell. The second step is fetch the corresponding TID list for each fragment from the fragment cube. Let's begin with the fragment cube AB. So in the fragment cube AB, we will see A2B1. A2B1. So A2B1 4 and 5, very good. So A2 B1 4 and 5. It is clear why A2 and B1 are in TID 4 and 5. It is clear? Okay, after that, for C, we have only the value C1, and C1 exists on 1, 2, 3, 4, 5. So C1 exists on 1, 2, 3, 4, 5. Okay? After that, E. So for E, we have how many possible values? For E, 3 possible values. We have E1, E2, and E3. Yes. So E1 for 1 and 2, E2, 3 and 4, and E3 for 5. E1, 1 and 2, E2, 3 and 4, and E3 only 5. After that, the third step is to intersect the TID list from each fragment to construct instantiated base table. So the intersection here gives us C1 E2 with the list 4. The second intersection is five here, and 5 here. So C1 E3 with 5. It is clear. So this is the base, the instantiated base table. This is in blue, the result of instantiated base table. After that, we will compute the data cube using the base table with any cubing algorithm. First one has A1, B1. No, A2. A2, B1. A2, B1. A2, B1. A2. So A2 and B1 are instantiated value, fixed. We cannot modify these values. So 4 exists on A2, B1, exists on C1, and exists on E2. After that, the result is 2 dimensions. Only the inquired dimensions. Only the inquired dimensions. That means the dimensions with the interrogation mark. So what are the interrogation mark here? C and E. It is clear? Good. Let's move now to processing advanced queries by exploring data cube technology. Statistical surveys and OLAP. So statistical survey is a popular tool to collect information about a population based on a sample. We talk about sampling. For example, TV rating, US census or election, and this tool, it is a common tool in politics, health, market research, science, and many more. And it represents an efficient way of collecting information. Why? Because data collection is expensive. So there are many statistical tools available to determine the validity of this sample. For example, we can talk about confidence intervals and hypothesis tests. So confidence intervals tell us how reliable result is. And the OLAP, the multidimensional analysis on survey data, this is the question. Can I perform OLAP on survey data? So it is highly desirable, but can it be done well? This is the question. So this is an example of a sample. So sample versus the whole population. In this example, we have age, education. So many students in high school, in college, and graduate with different age, and this schema or this figure presents a sample of a population, just a sample of this population. So the question is, can I make or can I perform OLAP on this population? So OLAP traditionally has the full data population on hand, yet with sample data we have only a small subset, just a small subset. So there are some challenges or problems. For example, if I make a drill down of this data, so if I make drill, what's the meaning of drill down? I will get a subset. Okay, so I make a drill down of the data. It is easy to reach a point with a very few or no samples. This is an example. So in this example, I can, for example, get a few like this. Very few samples or no samples. Also, OLAP is not equipped with confidence interval. This is a second problem. Yes, but with the statistics tools, when we create this sample, there are some statistical tools available to determine the validity of this subset. So for example, in statistics, we can calculate the confidence interval. And this confidence interval tells us how reliable a result is. But when we perform OLAP on this survey, we can find a problem like this. It is clear? So for example, what is the average income of 19-year-old high school students? This is a question. And normally we have to return not only query result but also confidence interval. So how we can compute confidence intervals in OLAP context? And here, for example, we have no data. Why? Because we performed drill down with OLAP. So not exactly no data, but no data in subspaces in cube. So this is the problem of performing OLAP on survey data. It is clear? Any questions? So what's the meaning of confidence interval? We write confidence interval at, for example, x mean plus or minus TC multiplied by the deviation, the standard deviation of X. So X is a sample of data set, X bar is the mean of the sample, TC is the critical T value calculated by a lookup, and sigma X is the estimated standard error of the mean. For example, we write $50,000 plus or minus 3,000 with 95% confidence. This is the meaning of confidence interval. That means the mean is $50,000. We can so the value can be between 47,000 and 53,000. This is the mean of plus or minus 3,000, and 3,000 in this case represents the confidence interval. So return answer in the form of confidence interval indicates quality of query answer, and the user can select desired confidence interval. So for OLAP, the problem of the samples can be resolved by query expansion. So for example, the queried cell 90-year-old college student contains only 2 samples. So the confidence interval is large. Why? Because we have a small sample size and a high standard deviation with samples. So small sample sizes can occur at relatively low dimensional selection. So we will collect more data, is expensive, or we can use data in other cells, maybe, but have to be careful. So this is a query expansion, and there are 2 manners to make query expansion. So we can make intra-cuboid expansion. Here we expand the sample size by including nearby cells in the same cuboid as the queried cell. So this is an example. For example, here, this is an example of intra-cuboid expansion. So in the same cuboid, we will add some samples from the nearby cell. This is an example. So combine other cells' data onto boost confidence if share semantic and cube similarity, and this manner is to use only if necessary. So cell segment similarity, some dimensions are clear, for example age. Some are fuzzy, for example occupation. So occupation is not very clear. May need for this reason we may need domain knowledge. The second manner, any question here for intra-cuboid expansion? So the second manner, so for example here, for intra-cuboid expansion, for our question, expand query to include 18 and 20 years old. This is the first manner of intra-cuboid expansion. Or the second manner for intra-cuboid expansion, we can expand query to include high school and graduate students for 19 years. So this is the first manner. The second manner to increase the number of samples or we can make this manner. So in this case we expand the age and in this manner we expand the education. It is clear for intracuboid expansion. The second manner is intercuboid expansion. This is the second manner. So for the second manner, in this case, the expansion occurs by looking to a more general cell. For example, in our case, a more general cell is age cuboid or occupation cuboid. For example, the cell in the 2D cuboid age occupation can use its parent in either for the 1D cuboid age or the 1D cuboid occupation. So if a query dimension is not correlated with cube value but is causing small sample size by drilling down too much, we can remove dimensions, that means generalize to star and move to a more general cuboid. We can use the two sample t-test to determine similarity between two cell across cuboids. Any questions? Multidimensional data analysis in cube space. This is our last topic in this chapter. So data cube greatly increases the analysis bandwidth, and there are 4 ways to interact OLAP styled analysis and data mining. The first way is to use cube space to define data space for mining. This is the first way. The second one, use OLAP queries to generate features and targets for mining. The third one, using data mining models as building blocks in a multi-step mining process. And the fourth way is to use data cube computation techniques to speed up repeated model construction. Any questions? So cube space data mining may require building a model for each candidate data space, and sharing computation across model construction for different candidates may lead to efficient mining. Let's move now to complex aggregation at multiple granulators. So multi-feature cubes, we want to compute complex queries involving multiple dependent aggregates at multiple granulators. So grouping by all subsets of item, for example, region, month, find the maximum price in 2010 for each group and the total sales among all maximum prices tuples. So to respond to this query, we have to write select item, region, month, max price, sum r dot sales from purchases, where here equal 2010. After that, we have to specify we will cube by what. In our case, we will make cube by item, region, month, such that r dot price equal max price. So this is a complex aggregation at multiple an example of complex aggregation at multiple granulators, multi-feature cubes. Yes, cube by. Any questions? Sorry, here R in cube by statement what it represents. So in this example, when we write a select item, region, month, max price, sum R dot sales, here R is just a moment please. Maximum price in 2000 and the total sales amount. Here R represent all the prices. Normally, all the prices. Just a moment, please. So R represents a grouping variable. The variable R is a grouping variable ranging over all tuples in group GI that have a price equal to max GI. So this is a detail. You can find it in the textbook in the page 231. You are welcome. Okay, I need to save the attendance. One moment, please.